Over the course of this chapter, over several different segments, we're going to be talking about 4 very common types of aqueous reactions. Precipitation reactions, where you have ions combining to produce a solid that is not soluble. Acid-base reactions, where you have exchanges of protons and hydroxide ions to produce salts and water. Gas evolution reactions, which produce some sort of volatile gas that comes off, and oxidation reduction reactions, where you have electrons that are moving back and forth between the different molecules involved. So those are the types, and we're going to, before we talk about any of these, an important concept that we want to work with is this concept of molecular equations, ionic equations, and net ionic equations. So the molecular equation would be something like this. We don't explicitly write out the water, except that, we have it in, the phase that it's in, that we note this being, aqueous. We know that the phase is aqueous. But we don't write out the compounds as they, actually are in the solution. We write what we put into the solution. So for example, here, PbNO3, 2, we put that into the aqueous solution. We put in potassium iodide, and those are the reactants we put in, and we say, well, we're going to get out lead iodide and potassium nitrate. But really, there are no molecules of lead nitrate in the solution because lead nitrate is soluble. It breaks apart into its ions. So it's a little deceptive because there are no potassium iodides in there. They're actually potassium and iodine going about their merry way, floating around, not really interacting with each other that much. So that's the molecular equation. The ionic equation, or sometimes the complete ionic equation, would be where we more realistically represent it by putting all of the compounds that are soluble, break them apart into their ions. We don't do that for weak electrolytes, just for strong electrolytes. And so in this case, because potassium nitrate is soluble, the ionic equation is Pb2 plus aqueous plus 2NO3 minus aqueous plus 2K plus aqueous plus 2I minus aqueous, because those compounds are all completely soluble, reacts to form PbI2 solid. Now that is not broken apart into ions because in water it's insoluble. You actually do have molecules of PbI2 because it's ionic. You actually have like crystals of PbI2. So it's not accurate to say that it's free-floating ion anymore. But then as a product, 2K plus aqueous and 2NO3 minus aqueous, because those do remain in solution. So this is the ionic equation. Now, one thing we've got a chemical reaction here, but we have some things that are on both sides of the chemical reaction. You've got the nitrate is on both sides, the potassium is on both sides. So even though we originally put in potassium nitrate and we say that we put in lead nitrate, and we have a product that's potassium nitrate, that's not very, that's hiding what's going on. The reaction that's going on is lead and iodine reacting, lead and the iodide ion reacting to produce lead iodide. The nitrate really has nothing to do with it. The only thing the nitrate has to do with it is, that's what came along with the lead to begin with. That's how the lead went into solution, but it's not involved in the actual reaction. It's just standing around doing nothing. It's a spectator. And so we call those, the net ionic equation, we remove anything that appears on both sides. We call those spectator ions because that's about the best word you can have for it. They're sitting around, they have nothing to do with the reaction at all. So that for the net ionic equation, we remove anything that does not participate in the reaction, which is usually indicated by the fact that it appears on both sides of the reaction. So that's molecular, ionic, and net ionic equations. So what the right one, you'll see, all of these used frequently when you'll see molecular equations and net ionic equations frequently used to describe reactions. You have to understand what the real context is and what it's telling you about what's going on. People usually don't write out the complete ionic equation except when going from the molecular to the net ionic equation, because why would you write out extra things if you don't have to? But it's useful to write those out to be able to explicitly recognize what's going on, and especially going, it's a bridge going from molecular to net ionic.